I see. Uh-huh. Okay. Okay, fine.
Today the faculty is closed, no?
Yes, yes. Здрасте. Yeah, but actually it's a common thing that indeed in public holidays the faculty is closed, but we can ask if we want to still have classes, then okay. Then it's fine. Okay, so yes. So last time what we did, if we have some compact Riemann surface and some point P, then we then constructed some sequence of numbers such that there is a basis in the space of holomorphic differentials on X such that the order of omega I at the point P is equal to Bi. Yes, and then we proved that if P is a Weierstrass point, then the weight is equal to sum of Bi's minus G times G minus 1 over 2. Yes. Yeah, our goal for today is to prove that to prove that the weight is less or equal than G times G minus 1 over 2. Okay, for this, yeah, actually we have to prove some theorem about some general theory about some general theorem about divisors. Yeah, for this, let's introduce several notions. So definition. Okay, so suppose X is a compact Riemann surface. And we have some divisor. Then, yeah, there are three definitions. First one, so D is called positive, is called, maybe we actually had this definition, but okay. D is called positive. Okay, maybe I even write like this. Then D is called positive if this is a positive function, D of X for any X. So obvious definition. Second is called effective if D is equivalent to D prime, where d prime is positive. Is so effective divisor is a divisor that is equivalent to a positive divisor. And the third one, D is called the special if the dimension of H1 XOD is greater or equal to 1. Yes, okay. So three notions. Positive, so effective is a divisor that is equivalent to a positive, and special if the first cohomology group is non-trivial. You remember what this means, D equivalent to D prime?
The difference is a principal.
Yes, yes. Okay, then then there's a then just remark to confirm that everybody remembers it, that if basically if two divisors are equivalent, then basically all the cohomology groups are the same. So if D then HI then basically OD is equivalent, is isomorphic to OD prime. So in particular, and in particular all the cohomology groups are the same. HI X O D prime. Okay. So this the sheaves are isomorphic, and then particularly all the cohomology groups are the same. Okay. Then there is a small lemma. Actually, saying when a divisor is effective. So D is effective if and only if H0 XOD is not 0. Proof? Any remark? So in one direction it's easy. So actually both directions are easy. So D is effective. So D is equivalent to D prime, which is positive. But then if you have a positive divisor, then of course the function 1 belongs to O D prime of X. So the dimension is not 0. Yes. So if your divisor is positive, then all constant functions belong to this group. Yeah, just by definition. So this is a constant function. Yeah, just it has it takes value 1 everywhere. And then the converse is also clear, because H. So you have OD. You take. So we take non-zero F from this group OD of X. But then actually what it means that F belongs to this group. So it's a meromorphic function such that its divisor is greater or equal than minus D. Yeah. So then we then D prime is equal to plus D is equivalent to so you just take this sum, the principal, the divisor of F plus D. Then by definition it's a positive divisor, and then by definition it's equivalent to D prime. Okay, any questions? So basically these are symmetric definitions. So divisor is called effective if the zeroth cohomology group is non-trivial, and it's called special if the first cohomology group is non-trivial. Okay. Yes. Then there is another lemma, a simple lemma. Describing how to compute the dimension of this group OD of X. So suppose D is positive. Is positive. And okay, suppose you have some finite and S finite set. Finite. So basically S is some finite set containing all the points where D is non-zero. Then, and okay, let's suppose we have some number. Then dimension OD of X minus 1 is greater or equal to T if and only if for any distinct points P1 PT on X without this finite set S, there exists non-zero function from our space OD of X such that it vanishes at these points, such that F of Pi is 0. Yes. Yeah, so you have your Riemann surface X, and this is some finite set S containing the points where your divisor is non-zero. Yeah, then the dimension of this space -1 is greater or equal to t. If and only if for any t points, you can always find a non-zero function from f, okay, not identically zero, such that it vanishes at these points. Yeah, it's in easy lemma. Yeah, so what you have in one direction. Suppose that then it's greater or equal to t. So, yeah. So if dimension is greater or equal than t minus 1, then the dimension of the space of functions that vanish f1 f of p1 pi is greater or equal than what? Suppose you now add constraints that your function should vanish at the first I points. So then what can you say about the dimension of the resulting subspace?
The dimension.
Yeah. So you know that the dimension of ODX is greater or equal than t plus 1, but then you want to look at the functions that vanish at the first I points. Then what can you say about the dimension of this space?
We want it to be greater than 1.
Ah, sorry. Yes. T plus 1 and what? Minus I, yes. Yeah, because basically if you say, for example, just for I equals 1, you want to add the constraint that f of p1 is 0. Then, okay, just one linear constraint. Then the dimension can drop, the dimension can be the same or drop by 1. Okay, adding one more point, so adding one more point, it either adds constraint or it doesn't add anything. So the dimension can drop at most by I. Yes, but then I mean but then you are done. Yeah, because then for I equals t, then you get 1. Yeah? So then this is equal to 1 for I equals t. And this is what you want. Yeah? So you want to look at the functions that vanish at all these points. The dimension of this space is at most 1. And then, okay, then such a function exists. The converse statement, yeah, it's also easy. Suppose that for any distinct points, yeah, okay, so suppose, let us prove by contradiction. So suppose the dimension of OD of X is less or equal is less or equal than t. Yeah, then what you say? We say that yeah, then yeah, okay, then take a yeah, okay. What you say? You say that yeah. Oh, suppose is equal to m. That is less or equal than t. Then yeah, there exists oh, yes, okay. So then there exists a non-zero f1 0 O d of x such that sorry. You can just say the following. So take arbitrary non-zero okay, then since it is not zero, then there is a point where it is not zero. Yeah, then choose p x without this finite set such that f1 of p is non-zero. Yes, then yeah, then yeah, consider the subspace. Okay, f1. So consider the space of functions f o d of x such that they vanish f of p is equal to 0. So you choose some function, choose a point where it is not 0, and then consider all the functions that vanish at this point. Okay, then the dimension of this space is equal to what? To m minus 1. Yes. Then yeah. Then again choose take arbitrary function f2 not 0 in this space. So take an arbitrary not 0 function, then and choose some function, some point. Choose p1, so it will be a point p1, and choose p2 in x without s, such that f2 of p2 is not equal to 0. Yes. Then p1 is automatically not equal to and p1 is not equal to p2. Yeah. Then define v2 as the space of functions such that f of p1 is equal to 0. Yes, and then you continue in the same way. Yeah, then you continue. And then what you so continue. So then we obtain so distinct points P1 PM yeah, such that yeah, so you define this space, and then the dimension of this space is m minus 2. Yeah, and then you construct distinct points P1, PM such that the dimension of the space of functions OD of X such that they vanish at these points is equal to 0. And so this is a contradiction. So this is a contradiction. Contradiction. Yeah. Okay. Again, this is a contradiction. So again, briefly, what we do. So you just consider an arbitrary function from the space ODX. So you want to go to get a contradiction. So to construct T points such that there is no such function. What you do, you take an arbitrary function and then choose a point where this function is non-zero. Then this means that the space of functions that vanish at this point has dimension exactly m minus 1. So you look at all functions that vanish at this point and choose a non-zero function from this space. So this function doesn't vanish at some other point. Then you take all functions that vanish at these 2 points. It has dimension exactly m minus 2. And again, in this space you choose a third point, choose some function non-zero, and choose a point where this function is non-zero. And then yeah, the space of functions that vanish at these 3 points is a space of dimension m minus 3. Okay, and then you get PM points. And so by this procedure you get m points such that the space of functions that vanish at all these points is trivial, so it has dimension 0. But this contradicts that for any t points, m is less or equal than t. Yeah? That for any t distinct points, you can choose, you can find the function, non-trivial function that vanishes at these t points. So is the proof clear? Okay, and then yeah, this simple lemma. We have proved this simple lemma, but using this lemma, we can prove some theorem, which even has a name. It's called Clifford's theorem. It says the following. The first part says that if divisors d and d prime are effective, then the dimension OD of X plus dimension OD prime X is less or equal than the dimension OD plus D prime of x plus 1. Yes. Yes. And then the second part says that if D is effective and special, then you can bound OD of x, the dimension of OD of x. Then this dimension is less or equal than the degree of D over 2 plus 1. And special, then you have this. Proof. Yes, actually it's an easy application of dilemma. Why? Because, okay, let us prove the first part. The first part says that the dimension of OD plus D prime, so we want to prove that this is greater or equal than so we subtract 2 from both parts. So we want to check this. Okay, and then okay, let us denote this by t, and then this by t prime. So you want to prove that that this dimension -1 is greater or equal than t plus t prime. Yes, yeah, okay. Strictly speaking, what you should do without loss of generality, so we can assume D prime are positive. Okay, then choose S, because we want to use the lemma that we have just proved, and this lemma we had this finite set. Okay, and then this will be just the support of D union support of D prime. Yes. Okay, then we use the lemma that we have just proved. Use the lemma. So we want to check that this number is greater or equal than t plus t prime. So for t plus. So for we have to check that for any t plus t prime points, we can choose a non-trivial function that vanishes at these points. So let p1, pt be arbitrary
Sorry, why we can assume the vice versa are positive?
because this, as I said, the dimensions do not change here. So if you replace here d by some equivalent divisor, then this dimension will be the same, because just the shifts will be isomorphic. So let with consider arbitrary points from x without s, the arbitrary points. Yes. Then, by the lemma, there exists non-zero function f1 in OD of x such that f1 p1 f1 of p t is equal to 0. So there is a function that vanishes at the first t points. And again, by the lemma, so and there exists a non-zero function f2 in OD prime of x such that f2 of p t plus 1, f2 of p t plus t prime is equal to 0. Yeah. Then the product, then f1 times f2, the product is not 0, and f1 f2 of p1 p t plus t prime is equal to 0. Yes. So this is all. Yeah. So for any t plus t prime points, you have to find a function that vanishes at these points. So you find the function that vanishes at the first t points, find the function that vanishes at the last t prime points, and then multiply them. Yeah, and then you get what you want. Yeah, any questions about the first part? Okay, if there are no questions about the first part, then we go to the second part. Yeah, so D is effective. It's special. I mean, it's special. Yeah, as we as we defined, this is equivalent to the fact that h1 of x OD is not 0. But then, by the Serre duality, we know that h1 of this guy is h0 of x omega minus d. But we know that omega minus d is isomorphic, this sheaf is isomorphic to OK minus d, where k is a canonical divisor. So, you see, we have obtained that h0 of OK minus d is non-zero. So basically, this is equivalent to the fact that k minus d is effective. So basically, you see, yeah, there's this dual thing. Yeah? So d is special if and only if k minus d is effective. Yes. Okay, and then you just then apply part one for d for d prime equals k minus d. What we get? So you get that the dimension OD x plus dimension O k minus d x less or equal, then the dimension of O, you take the sum, but d plus k minus d is OK plus 1. But this is g, yes? OK is omega, so this is g. Yes. And then what?
By the lemma we can say the last one, no? Like there's a function but in OD plus D prime.
Yes.
So, and we can also say like because it's there that it's in each of those, but why, how do you deduce that there's F1 and F2? Like by lemma.
Yeah, well, again, by the lemma. So you see, this dimension is equal to t. Then for any t points, there exists a function that vanishes at these points. So this I here, this I.
But the function is in D plus D prime.
Yeah, but of course.
Is there,
Yeah, so we use, of course, I did not say it explicitly. Yes, indeed, you have that OD of x is inside, but basically, if you have F1 belongs to OD of x, and F2 belongs to OD prime of x, then this implies that F1, F2 belongs to OD plus D prime. Yeah, this I used.
So you apply the lemma twice?
Yes, twice, yes. Yes, so to be honest, it's a bit strange. So what you have, I think you have to apply Riemann-Roch. So you say that this is greater or equal then 1 minus g 1 minus g plus the degree of k minus d, degree of k minus d. Yes. But OK is omega is isomorphic to OK. Strange, I'm a bit confused. It was some simple computation. Maybe, sorry, or what, maybe we should do the following. So, OK minus D is and this is omega minus D of x. Yes, sorry. Yeah, this is omega minus D of x. But by the Serre duality, you know that this is isomorphic to H1 XOD. Yes. So then you write. So you write that OD of X, the dimension of OD of X plus the dimension of H1 X OD is less or equal than G plus 1. And then you use Riemann-Roch. Dim OD of X minus dim H1 X OD is equal to 1 minus G plus the degree of D. And then you sum and get twice the dimension OD of X is less or equal than G cancel each other, and then you get 2 plus deg D. Yes, and this is what you wanted. Yes. Any questions? Okay, and then we can prove this theorem about the weights of the Weierstrass point theorem. So we consider Riemann surface of genus greater or equal to 1, and suppose P is a Weierstrass point. P is a Weierstrass point. Then the weight is less or equal to G times G minus 1. Then the weight less or equal than G times G minus 1 over 2. And then the weight is equal to G times G minus 1 over 2 if and only if X is isomorphic to a hyperelliptic Riemann surface. Hyperelliptic Riemann surface. Yeah, now it just becomes just a formal computation. What we, yeah, again, the weight is equal to sum of BI's minus G times G minus 1 over 2. Yes. Yeah, remember, yeah, that I recall, yeah, so that we had a basis. Yeah, I use the notation that we had at the beginning, so meaning that we had a basis such that the order at the point P of omega I is equal to BI. Yes. Then, what is then the dimension? The dimension of omega minus BI P X. Well, what is it? what is the dimension of the space of holomorphic forms, such that they have 0 at P of order at least Bi. Ну да. Yes, it is G plus 1 minus I. Yes, indeed. So yeah. So B1, that's so recall then. And B1 is actually 0. So when I is equal to 1, you just consider the space of all holomorphic forms, and the dimension is G. And then, yeah, just by the construction, yeah. So when you go to from Bi to the next number, yeah, then the dimension drops by 1 exactly. So actually, yeah, this is by construction. Yeah, it's clear. Okay. Then, but then, yeah, again, by the CR duality, this is equal to the dimension of H1 X O Bi P. So in particular, I is between 1 and G, so this is equal to 1. So this is H1. So this divisor is special, yes? So Bi P is special. Is special. So apply Clifford's theorem. You get that the dimension of O Bi P is less or equal than Bi over 2 plus 1. Yeah, so it's a special, and obviously it is positive, yeah? So you can apply Clifford's theorem. Part 2 of Clifford's theorem. So you get this inequality, but then you apply Riemann-Roch. Yeah, so this is equal to the dimension of H1 X O Bi P plus 1 minus G plus Bi. But this guy we already know. This is this number. This is equal to G plus 1 minus I. So, what you get, you substitute here, and so G cancel each other. So you get 2 minus I plus Bi. So you get 2 minus I plus Bi is less or equal then less or equal than Bi over 2 plus 1. So you move Bi to the left hand side, so you get Bi over 2 is less or equal than I minus 1. No, O Bi less or equal than 2I minus 2. Yes. So we get some non-trivial result that Bi is less or equal than Bi minus 2. Actually, if you think about it, it's a bit funny. Yeah, so we didn't do any deep things, so with just some elementary manipulations, but yeah, get some non-trivial result. Yes, and then you, yeah, then the rest becomes obvious. Then sum of Bi's is equal to so minus g times g minus 1 over 2, then is less or equal than twice 0 plus 1 according to this bound plus g minus 1 minus, yeah, and this is exactly g times, yeah, so part 1 is proved. But then, okay, part 2. Any questions about part 1? Okay. Yeah, actually, what is part 2? It says that the weight is this, if and only if hyperelliptic. So the one direction, we already know one direction. Yeah, so this one was homework. It was homework. It was some homework problem, a homework problem. Yeah, so I don't remember, maybe homework 5, where we discussed the Weierstrass point, or the weights of the Weierstrass points for hyperelliptic Riemann surface. Okay. The converse is also easy because, so if the weight, is equal to g over 2, it implies that in all these inequalities, these ones, we have equalities. Yeah. Okay, the weight is equal to, actually it's if and only if bi is equal to 2i minus 2 for all I between 1 and g. But then, okay, then I finish here. But then what you have that then. So in particular, you get that the dimension of O. So in particular, you get that. So in particular, you get that B2 is equal to 2. Yes. So what I want to say, yeah, to be more precise, what you mean, you see how we got this inequality. We used this inequality, yes. So actually, if these inequalities are equalities, if and only if all these guys are equalities, yes. So all these, yes. Star is equality. is equality. Yeah, so what we get? So you get that bi is equal to 2i minus 2. So in particular, you get that b2 is equal to 2. Yeah, that b2 is equal to 2. So b2 is equal to 2. And then from this, you get that the dimension of O b2 of p, so O2 of p, x actually I forgot, is equal to b2 over 2 plus 1, so is equal to 2. But then this implies that there exists a non-constant holomorphic f from x to cp1 of degree 2. Yes, exactly. So this means that this space has dimension 2 if and only if there exists a function with only one pole, and moreover the order of this pole is equal to 2. So there exists a non-constant holomorphic function from x to cp1 of degree 2. And then this implies that our Riemann surface is a hyperelliptic Riemann surface. Okay. Any questions? Okay. Then then corollary. Maybe we could even add the third part. Okay, corollary. Okay, recall that by Wx I denote the set of all Weierstrass points. The set of all Weierstrass points. And then corollary. So again, we consider Riemann surface of genus list 1. Then the first part says that the number of the Weierstrass points is greater or equal than 2g plus 2. So there are always many Weierstrass points. And the second part, the number of the Weierstrass points is equal to 2g plus 2, if and only if x is isomorphic to a hyperelliptic Riemann surface. Yeah, and yes, and this follows from the theorem, yeah, because sum of the weights of the Weierstrass points is equal to what? Sum of the weights of the Weierstrass points is equal to what? To what? Yeah. Yeah, so it is equal to g times g plus 1 times g minus 1, which is 2g plus 2 times g. Yeah. So, since the weight of each Weierstrass point is less or equal than this number, then the number of all points is at least 2g plus 2. But then the number of the points is exactly 2g plus 2 if and only if the weight of each point is g times g minus 1 over 2. Yeah, and then, yeah, by the theorem it should be a hyperelliptic Riemann surface. Да. И утверждение. Yes, very good remark. Yes, indeed, G should be equal to 2. Yes, because actually, if you have a complex torus, suppose G equals 1. What are the Weierstrass points on a curve of genus 1? No, yes. So no Weierstrass points. Yeah, I mean, you can explain this, yeah, at least by two arguments. First of all, the sum of the weight, what you can say, the sum of the weights is this, yes? So the sum of the weights is 0. Yeah. So, I mean, but you can also say that you know that a point is a Weierstrass point if and only if there exists a non-constant meromorphic function with a unique pole, and moreover the order of this pole is less or equal than g. But if g is equal to 1, then you know that there cannot be a meromorphic function with a pole of order 1. Yes, so indeed this corollary is true only for g greater or equal to 2. Yes, then this is correct. And then actually the main application is that each Riemann surface has finite automorphism group. But first there's a small lemma. Suppose what? Yeah, so suppose phi is some automorphism. And suppose that the number of fixed points is greater or equal than 2g plus 3. When I write x phi, I mean fixed points of phi. I don't know. Probably this is, I'm not sure whether this is standard notation. Okay, let me write. So you consider the points in x such that phi x is equal to x. Suppose the number of elements here is greater or equal than 2g plus 3. Then phi is the identity. Actually, non-trivial automorphism cannot have more than 2g plus 2 fixed points. No. You see, actually, this is a generalization for of the genus 0 statement. Yes, so you know that any automorphism of the sphere is determined by 3 points. Yes, uniquely determined by 3 points. So you see, So if your automorphism fixes 3 points, then it is trivial in genus 0. And then this is some generalization to Heidegger actually. Yeah. Yeah, and the proof is easy actually. By contradiction, suppose phi is not equal to the identity, then there exists a point such that phi x is not equal to x. Then we know that there exists a meromorphic function on x such that f has a unique pole at x, and S has a unique pole, and the order of this pole and the order of this pole is less or equal than what? What? No, you answer. There is a unique pole at x, and the order of this pole is less or equal than what? What can we say about any point? So if you have an arbitrary point, then there is all, we already used this argument several times. So for any point, there exists a meromorphic function with a unique pole at this point, and the order of this pole is not high. Okay, do you remember? Okay, who remember? Yes, g plus 1. Yeah, guys, I mean, we should remember this. It's very basic. Yes. It's very basic that for any point there is always such a function with controllable pole, and if it is g, if the order is less or equal than g, then it's actually Weierstrass point. Yes, yes, and then you see, then h, then the function h, which is f minus f composition phi, satisfies the following two properties. The first one, so it has two poles of order less or equal than g plus 1. And the second one, h, it vanishes. Okay, maybe I emphasize that it has exactly two poles. It has exactly two poles of order less or equal to g plus 1, and it vanishes at the points from this set, at the fixed point set. Okay, maybe I didn't indeed. This set I denote by x phi. It vanishes at the points from x phi. But then you see, so it vanishes at the points from x phi. So the sum of the orders of the zeros is at least 2g plus 3. Yes? But then we know by construction that it has exactly two poles of order less or equal to g plus 1. So the sum of the orders of the poles is less or equal to 2g plus 2. So you see, the orders of 0 is greater or equal than 2g plus 3, and the order of poles is less or equal to 2g plus 2. But they should be equal. Yeah, so this is a contradiction. So contradiction. Because the sum of the orders of the zeros should be equal to the sum of the orders of the poles. Yes. Yeah, so this completes the proof. Any questions? Yes, and then we can actually, yeah, we should finish, but now, but actually we need only a small argument to prove the following important theorem, saying that the automorphism group of any Riemann surface of genus at least 2 is finite. So theorem that if G is greater or equal than 2, then the automorphism group is finite. Okay, and then the proof is the following. So automorphism group X on the set of the Weierstrass points. Yes. So clearly, any automorphism maps a Weierstrass point to a Weierstrass point. So the automorphism group of X acts on the set of Weierstrass points. And so the automorphism group is finite if and only if the set of automorphisms that fix the Weierstrass points is finite. Yeah, so if and only if x phi yes, you want to consider, so these are just automorphisms that fix all the Weierstrass points. Yeah, so here I just write just the subgroup in the group of automorphisms that fix all the Weierstrass points. This is clearly a subgroup of finite index. So of course, and then the whole automorphism group is finite if and only if it's a subgroup. Huh? Just because you see, the automorphisms of X act on the set of Weierstrass points. So this means that you have a homomorphism from out X to the permutations. Okay, I write it in this way. So these are just this group of permutations of Wx. Permutations of Wx. Yes. And then I just want to say that here you have the kernel of this homomorphism, and this kernel, I mean the yeah. Then you of course if you have the number of conjugacy classes, I mean, and the quotient by the kernel is finite. Yes. Because I mean the quotient by the kernel is the image, yes, and the image is finite. And then of course this group is finite if we not leave this kernel is finite. Yeah. Yes. Yes. Yeah, so what I want to say, yes. So there are two cases. So case one, is when case one, suppose that the number of the Weierstrass points is greater or equivalent to G plus 3. But then you are done. Use the lemma. Then use the lemma. Yes. So because you see, now you want to prove that the set of automorphisms that fix all the Weierstrass points is finite. Okay, but the number of the you assume that the number of the Weierstrass points is at least 2G plus 3. But then this lemma says that if an automorphism fixes 2G plus 3 points, then it's automatically trivial. Yes. So actually this means that this subgroup is actually trivial. And case two is when, so you know that the number, there are at least 2G plus 2 Weierstrass points. So okay, so the case when the number of Weierstrass points is 2G plus is greater than 2G plus 2 we did. So the rest is the case when the number of the Weierstrass points is 2G plus 2. But then again, by this corollary, then X is isomorphic to hyperelliptic. Hyperelliptic. Yeah, but then I mean it's easy. It's just okay. Let us denote. Okay, let us denote this group automorphisms that fix the Weierstrass points. Okay, let us denote it, I don't know, by G. Yeah, so use the lemma, and so in this case you get just that G is just the identity, consists only of the identity element. Okay, then X is hyperelliptic. Okay, then consider. Let us check. Let us show show that G, in this case, so the group that fixes all the Weierstrass points, is just the group that has only two elements, identity and the hyperelliptic involution. Yes. So indeed, take an arbitrary phi from G. I mean, I just recall the picture. What is the picture? You have our, again, I usually draw it like this. Yes, so you have our hyperelliptic Riemann surface, and you have some degree 2 map to CP1. And you have this hyperelliptic involution. If you take some automorphisms that fixes all the Weierstrass points, then if you compose F with phi, then you get F. Yeah, this is very, very simple because you see, because we had some homework saying that this map from our hyperelliptic Riemann surface to CP1, this map of degree 2, is determined uniquely up to the action of the members group on CP1. But then F composition with phi is also a degree 2 map. And since phi fixes Weierstrass points, so it fixes at least 4 points in the image. So actually then, so these are both functions of degree 2. And yeah, since phi fixes the Weierstrass points, they should be equal. But then this implies, and therefore, if F composition phi is equal to phi, then phi x is equal to x. Phi x belongs to the set x tau x for any meaning that phi can map any point either to x or to tau x. Yeah, but then phi is equal to the identity, or phi is equal to tau. Because basically, if it maps, if phi maps, choose some point not equal to the Weierstrass point. If phi maps x to x, then it maps some small neighborhood x to a small neighborhood x. Yeah, and then by the identity theorem, phi should be the identity. And then, I mean, and also similarly, if phi maps x to tau x, then it maps some small neighborhood of x to a small neighborhood of tau x by holomorphically. And then, yeah, phi is equal to tau. Okay, this completes the proof in the case of a hyperelliptic Riemann surface. Any questions about this? Okay. Yes. Actually, so yeah. And then next time we will prove Hurwitz's theorem. So now we have proved that the automorphism group is finite, but actually there is some bound 84 g minus 1. We will do it next time. Yes, it's a bit funny. It looks like, yeah, I know. It looks like no, this. At least I think at first time it looks like this is some simple statement. Okay, and this is much harder. But at the end, actually, this is a very important step. I mean, first proving that the automorphism group is finite. Yeah, it's actually longer than finally proving this one. So this will be. This is not. I mean, having this is not so difficult. Okay, we will do it next time, and we stop for today. No, yes, it's actually a good question. It's a good question. So this bound, this bound out X is sharp only for some special genera. So only for some special G. Yeah, for the first few, for some special G forming some infinite sequence, forming an infinite sequence. Infinite sequence. So there is infinitely many G's such that there exists a Riemann surface exactly with this number of automorphisms. And this sequence is 3. Yeah, I remember five, the first 5, and so on. Yeah. So, for example, there are no genus 2 surfaces with this, with this number of automorphisms, but yeah, there is some special genus 3. Okay, yeah, that's all.